So now that we're done with the electric heat wiring diagram, I just want to remind you that there's one rule that I mentioned toward the end of the last video, and that was wires in a junction at a switch. On the leaving side of that switch, power flows in those wires the same way. So look at that wiring diagram again, and you'll see that L1 goes into the switch, and if the switch were to close, power is going to pass across, and it's going to go into that black wire toward the electric heat strip, and it's also going to go in the purple wire the same way. So that purple wire is going to be bringing power into the female plug and into another circuit that we're going to get into with the air handler. Before I get off of this completely, I also want you to look down at the bottom at the terminal block where we had L1 and L2, and I want you to notice that there's two wires on each side of power there. So there's two wires on the L1 and there's two wires on the L2. And for me, L1 is always leaving and L2 is always returning. So when I'm looking at this diagram and I'm imagining power leaving the terminal block on L1, just like on the switch, and here's my second rule, wires leaving a power source are going the same way. So both of those wires here, both of the red wires, are leaving L1, and for me that means both of the black wires are coming back to L2. So those are two rules to keep in mind. One is wire junctions at a power source, and the other is wire junctions leaving a switch. And with that said, let's go into the next diagram. Okay, so here's the air handler we're going to look at, and just to let you know, I take the cover off the top, of course, for this demonstration, but we talk about the electric heat kit, but it's not included in the air handler. There would be a plate right there, and you would have to undo 4 screws. This is just a piece of scrap metal I had because I've thrown the original plate away, but it's a thicker gauge plate. You would take that plate out the way and insert the electric heater kit that you chose to go in your unit in that open space there. 4 screws in the corners, no big deal. So why did I use the electric heat kit as the starting point for talking about wiring? It's just easier for me. And what we're going to go into now is just the air handler, because electric heat is an accessory piece. It's not standard on an air handler. It's not required. You can change the size. There's too many variables. So that diagram that we talked about is on its own. It has a female plug, but so does the original air handler. And this plug is one that I don't throw away. I put a zip tie on it and keep it over in the corner or whatever. But the original female plug is on this air handler diagram, and you'll see that it only has 2 wires, L1 and L2, because that's all the air handler needs is L1 and L2 on those 2 wires to bring power to the primary of the transformer and to the blower motor, which we're going to talk about next. So same plug, but when we get finished with this, you should be able to take the wiring diagram we talked about on the electric heat and add it to the wiring diagram for the air handler. Using everything that we've already talked about, rule 1, rule 2, okay? Take a look at this diagram, pause the video for a few seconds, and when we come back, I'm gonna walk you through the 2 high voltage loads on here. The first is the primary side of the transformer, and the second is this PSC blower motor that you have on here. So pause it, take a look at it, familiarize yourself with it, and we'll talk about how the circuits actually flow after that. So if you remember what I told you, flip-flop L1, L2. We did it on the electric heat kit. It happens here as well. Even though you don't see that electric heater plug there, it's still the female plug, but the air handler plug is what's visible here, okay? So my L1 and L2 still flopped and flipped, or flipped and flopped, whatever you want to say, and we can follow flow just like this. So primary side of the transformer first. See as power leaves L1 and it flows down the red wire or out of L1 into the female plug on wire or terminal 2, through to the male plug number 2, and down into the primary side of the transformer. If you follow through the winding itself, when you get to the end that they label C, it's not common, it's just the other side of that load. What you're going to see is the black wire goes back up toward wire 1 of the male plug, and then of course through to the female plug and back to L2. And that's it. So something you may have noticed there is when we got to the load that is the primary of the transformer, that winding, what you're going to see across the top of that is labeled 1, 2, and 3. Terminal 1 on the far left is labeled common. Then there's a number 2 and a number 3. 1 is always going to be used. It's always going to have that black wire there and connected to it. But terminal 2 and 3, if you look to the far right, just outside of the transformer little depiction, the little box, the component itself, you'll see 240. Tap 3 is for 240 volt power sources. Terminal 2 is a tap where if you had a 208 power supply like I do in the shop, we would actually move the wire off the default 240 volt over to the 208, and it would use less of the winding since we have a little bit less voltage, okay? So that's the primary side of the transformer, done deal. But look at number 3, or the number 3 terminal, and what you're gonna see is there's a junction of wires. So rule 1 I had dealt with junction of wires, leaving a switch. The second rule had junction of wires, but leaving a power source or returning to it. Here's another one. It's the last rule that I have for you. What do you do with a junction at a load? You can cover that component with your finger or just ignore it in your mind. But when you have a junction at a load, the flow that brought power in that circuit, the direction that that wire, in this case the red wire, brought power down to terminal 3, it's going to keep going as if the transformer was not even there. So the rule that I have with junctions at a load is the flow keeps going. If you were to look at arrows, it's going to look weird. One's going to seem to be coming and the other one going, but it's really the flow continues in the direction as if the, in this case, as if the primary of the transformer windings wasn't there. So that red wire that is not L1 power specifically keeps the flow of L1 going, and if we follow it, it's going to bring us into our second load, the blower. So how do I get power to the blower? That L1 come down the red wire, kept going on another red wire, okay, and into the normally open terminal of our fan relay on that board. You can cover that component with your finger or just ignore it in your mind, but when you have a junction at a load, the flow that brought power in that circuit, the direction that that wire, in this case the red wire, brought power down to terminal 3, it's going to keep going as if the transformer was not even there. Just a little bit of information about this PSC motor. Red, blue, and black are the 3 speeds for the motor. Red is low, blue is medium, black is high. So we have to keep that in mind because we're not going to use any of those wires. That is the speed determining factor here. Whichever wire we put on the relay to get power is going to affect our blower speed. But if you look off to the right of that blower motor, you're going to see a purple wire. PU, purple. That is our way back. So L1 down the red wire brought it to the switch, the normally open switch. That's the control for the blower. Came out the common terminal, went to the motor itself, that's the load, and now we got to bring it back. So that purple wire, if you follow it, is going to go up, make a couple 90-degree turns, and you'll see the purple goes back and makes a junction on the common terminal of the primary winding of the transformer. So what does that mean? Rule number 3 again. Junctions at a load, you act like the load's not there. It keeps the flow going back. Okay, it's just keeps going the way it was. So as you bring that purple wire and it arrows kind of down to that terminal, it takes a sharp turn right back into the black wire and we've already established a flow in that, and if you pay attention, you'll see that it actually fits, okay? So that is the flow for both our transformer and our blower motor. Now let's switch gears and go low voltage. So first you have to find out where the low voltage comes from. And in our case here, we know that it's the 24 volt side or the secondary side of the transformer. Pay attention to that. You'll see 24 volts listed here at the bottom of the transformer winding on the secondary side. And you'll see terminal 4 and 5. 5 is grounded. So that gives us an indication of what side of power we're dealing with there. I would call that the common side. You'll typically see that on a Goodman air handler, and there's nothing wrong with it. Common is worth 0 volts, and ground is worth 0 volts, so there's no conflict of interest. R has the power. So let's go to terminal 4, which is where our red wire is, and let's follow the flow. It's just like an L1, except it's low voltage, so it's R. So power's coming out of terminal 4 there, and it's going down that red wire, and it's going up and into the circuit board. This board is what Goodman calls a EBTDR, electronic blower time delay relay. It's a fan circuit board for our PSC blower motor. So power goes in on the transformer R. It actually doesn't show it, but there's a fuse that it goes through next, and then power comes out on that red wire and basically goes straight up, and you can envision the thermostat being there. It says that there's a strain relief, and that's on that top cover that I removed on the air handler just a minute ago. But this is where you would have your actual field wiring for your thermostat wires, going to your outdoor unit, to your thermostat in the hallway, whatever. Everything, all those wires are basically meant for thermostat connections, but there's one that's missing, and that's the yellow. Because this is an air handler, it has nothing to do with your outdoor unit and your contactor or your compressor, so you're not going to see it, but you can envision it here. Something I tell my guys is when you're looking at diagrams like this, red or power is the only one going into the thermostat. The way that I envision flow, every other wire is coming back out. So I don't have a rule for that, it's just something that makes sense to me. So red power is going in there, but what if it's a digital thermostat? Well, they use blue down here on the common side of the secondary power source, so I'm going to use blue, and let's see how it goes. Imagine blue is returning back from the load that is the thermostat, and you can follow it. Blue goes down, goes into the common on the board, loops around to transformer common, and comes back into our secondary winding and completes the path. So blue is our common. And another thing here, look at that, we have a junction on that return side of our 24 volts. So I don't know where that other blue wire is, but junctions at a power source, they're either both leaving the same way or they're both coming back the same way. I know that this is returning back. So whatever this blue goes to is coming back to return and complete that circuit. So let's pay attention to green. Green, G, indoor fan. Green comes down, goes into the G terminal on the board. No big deal. That's the indoor fan relay coil going to the fan board. So we're good there. What about white? White comes down, is leaving the leaving the thermostat, and it's going to go into plug number 6 or wire number 6 of the male plug. But there is, on this diagram, there is no wire number 6 on the female plug. Now you have to switch back to the electric heat diagram and that female plug. And you'll see that wire number 6 has a white wire on it that goes to the heat sequencer relay coil, or the heat relay coil, or the heat contactor coil, or whatever. It's a 24 volt load. Blue, right, completes or is the common for that, so it's going to return back. So blue comes back through wire 4 of the female plug, and look at that, goes into wire 4 of the male plug, which is a blue wire, comes down a couple 90-degree turns, and goes right back to the common side of our transformer. So it fits. What about brown? Brown, just like white in this case, except that you have to have a big enough electric heat kit. In our case, we would need 2 heat relays in it. And since I don't have two white wires here, they go brown for the second stage. So that brown is going to come up, go to wire number 5 of the male plug. And on a larger heat kit, wire number 5 would go to, on the female plug, would go to a second heat relay coil. And blue would be the common for it as well, because they would be junctioned together and have that return side back. That's pretty much the high and the low voltage. Hopefully it makes a little bit of sense. If you have any questions, ask me. There's only one thing I'd tell you that I just realized I skipped, and that is a high voltage circuit for the blower. Look at that purple wire. Way back when I told you rule number 1, okay, was junction of wires leaving a switch. That purple wire left that heat relay switch, and it brought L1 power into wire number 3 of the female plug. If I follow that through to wire number 3 of the male plug, you'll see that purple wire is bringing power into the normally closed switch on our blower relay. If that switch were to stay closed, since it's normally closed, power would loop around and come out the common and go into the red or whatever speed we have, and we've already mapped that blower circuit out. So it's a redundant safety that brings on the blower whenever the heat strip is called for. So just in case the G doesn't energize, we still have a high voltage path to turn the blower on. So I hope this helps. Just remember the couple rules I put out. Rule 1, wires in a junction on a leaving side of a switch, flow is going the same exact way. Power's in a junction at a power source. If they're on the hot side, the L1 or the R, they're both leaving. If they're on the L2, the neutral, or the common side, depending on what voltage you have, they're returning for me. And if you have, well, rule number 3, junctions at a load, okay? You're not trying to power the load, you're trying to basically piggyback off of it, so the flow would be as if that load is not even there. It's a continuation. So pay attention to those. See if you can get them in your head. I hope it makes sense. If you have any questions, let me know.